Hello, my name is Rheagan Frantz, and this is my tutoring video for EDTP 645.
Hi, I'm Audrey Cooper. I'm a senior at Altus High School, and I am reviewing for the math portion of the ACT.
What we're actually doing is we're using a workbook to go through upper level algebra, so like mostly like a review type of thing. Okay, so looking at this first lesson. Okay, so we talked about function, we talked about domain and range, the independent, the dependent. Okay, so vertical line test. Have you heard of that before?
Yes.
Can you tell me what you remember?
The vertical line test on the Cartesian plane, when you have a vertical line through it, and if it cannot touch it more than once.
What's it?
The line.
The line, which is a function,
yes.
right?
Yes.
It's a function. So a function is such that you can't have like two answers for any one x.
Yes.
Right? Do you know what it would look like? What a graph would look like that was not a function?
It would be curved. It would touch the vertical line in more than one place.
Like, for example, like a circle.
Yes.
Right? It fails the test. Can you think of anything else?
An S.
Yeah. A lot of times we have these inverse functions. Look at that. It's a parabola, but it's turned to the right. I reflected it. Yeah, and so they're not a function anymore. So anything where you take that straight line and it hits any x, there's only one y value. Not 2, not 3, only 1. That makes it a function. So this is kind of an important little thing, and it's nice that they have this thing that they thought for people. I mean, really? Okay, I'm sorry for that interruption. The graph is not a function. The graph is a representation visually of a function, and we use it as a tool like a calculator. Yeah. I know I'm making my sing-song head. Okay. So then they would give an example, and this is a straight line. How can you tell it's a straight line? I look at the variable. So what's the exponent of the variable?
Just
1. Yeah. Okay. So if you have a line where the variable, one variable, not two variables, but one variable, and the exponent is 1, it's going to be a straight line. If the exponent were 2, it would be a.
I have not been over this.
Oh yeah, it would be like a parabola.
It would?
Yeah, the squared function. Do you know what the cubic function looks like? It's like this. It's like an S.
Okay.
Yeah. So what's really cool is that's a straight line. It crosses the x-axis exactly one time. Right? This is a cubic. It crosses the x-axis 1, 2, 3 times. Guess what a square function? How many times would it cross the x-axis?
2. Yeah.
And that's what finding the zeros is, or solving for the equation, or solving. And we have a lot of phrases that actually mean the same thing.
Okay.
So then it talks about how do you evaluate. Well, you substitute some value for x, and then you get an output, a value for y, right? And then I think you know how to graph it. And they have right here the absolute value function as an example, which is kind of a tricky example. Don't you think, the absolute value function? Like, I kind of want to talk about that just a tiny bit. Okay. All right, so let's just make a little t-table, okay? Here are my x's, and these are my y's. And you remember I like to use the same spots. Okay, so when x is 0, y is also 0, right? Okay, so what about 1? It's 1, 2, 3, and so yeah, it's the same for the negatives, right? When x is negative 1, it's still 1, 2, 3. So this is what they have. This is called set notation. When x is greater than 0, the value is x. And when x is less than 0, the value is negative x. Because if you said negative 1, negative 1 is 1. Negative 2 is 2.
Yeah.
So this is also true, this description, but you've never seen it like that, right? it's just kind of interesting. I think that the absolute value, another easy way to think about it is
the distance from 0.
Yes.
Yeah.
The distance from 0. That's a good one.
Exactly what you just wrote.
Oh, yeah. Yeah, it's so funny they go into an application for compound interest. This is kind of like a deal.
Where did that come from?
Well, what they want to do right now, what is the trend in math, is to go from this theoretical idea, like we just talked about the line, and then go right into a real world situation so you can feel, oh, math is useful, like, for all kinds of things, not just for being, it's not just a math game that we play in the classroom and then we go out, it's not useful for anything.
Compound interest is,
like, what should we do when it goes off like that? So now it's stopped.
No.
It's not stopped?
Just move it away from the little square.
Okay.
If it's not on that and you click it, then it won't do anything.
Okay. Okay. So, what did they do here? 100 plus 100.5. Oh my gosh. This is the actual...
Yeah,
okay.
I did this in personal financial literacy.
Did you?
Mm-hmm.
Okay. Okay, we use the letter t time from the independent variable. You know, that's really commonplace. That t time is the x. Suppose you invest $1,000 in a bank. That's the principal. And it pays 5% interest compounded annually. They don't give you the equation for that. Do you remember the equation for compound interest? Simple interest or compound?
No, I don't, but I can probably just figure it out.
Well, that's all right. They're not even requiring you to do that in this particular situation. It says, for the first is compounded
Well,
annually.
it says T years. It doesn't give you. It asks you a question, but doesn't
How much
give you-
money do you have to after T years?
Yeah. And then they.
Oh, well, they're asking you to write the equation.
Oh, okay.
See? So they do 100 plus, 1,000 plus 1,000 times 0.05, which is the interest, right? So you get the principal plus the interest. And then, so then they like did the reverse of the distributive. And so they wrote this as the next level, 1,000 times.
Okay, I thought, okay.
It's like a reverse. They took
so-
out a common factor, which is 1,000.
Okay.
And they came up with that. That's why you see principal times 1 plus the interest. And then, let's see, right here, they combined 1 plus 0.05 to 105. And so then, okay. So then for the second year, right, because this is the first year. So this is what you have at first, and this is the second year. Okay. And they just keep going.
Yeah, it keeps piling up.
Right, and they come up with this equation. You notice how t is in the exponent?
Yeah.
That is totally not linear at all. That's the exponential relationship. That's a lot more complicated. That's interesting that they took that as the example. But again, that's what I'm saying is that they really want you to...
Pitfall.
Okay. Although we usually write y equals f of x for a typical function, different letters are often used.
The underlying concept is the same. Okay. But
Do you find it to be a pitfall, though?
I mean, sometimes it
You
might
get
trip
confused
me up.
by
Yeah,
that.
especially if I'm like on the ACT, I'm trying to work really fast because there's only 60 minutes, you know. And I'm trying to
Do you know,
That kind of
like the... So you got x, you got y, and you got z. And those are your most common variables. But we also use u, v, w. We use
U and
s.
V are terrible.
We use s, t. These are really common variables. So we pick these letters that are at the middle and at the end to be our variables.
Oh, also A, B, and C. I see.
Well, but a, b, and c are never variables. What are they?
Oh, they're in the...
They're coefficients.
Yeah, they're coefficients. You're right.
Yeah. Isn't that interesting?
Yeah.
Yeah. Okay. So, anyway, here are some problems. I feel like that you could do this. I see number 2 is a little bit trickier. Why don't we just do, like, the first one, it says evaluate for h of 2. Can you see it well? Yeah. Okay.
If each specified value of the independent variable below and simplify. Alright, so Okay, when it gives me this, is that saying that t equals 2 right there?
Right.
Okay, just making sure.
Because h is the wrap. It's the dependent.
So I substitute
it's the function.
Every time?
So like h is the function, and 2 is the independent variable.
So I substitute 2 in for t again.
Absolutely.
Okay, just making sure.
I mean, that's a good question because you asked it, but like that, I would never even have come up. Yeah, obviously, look at how h of 2 just looks like h of t, and 2 is in the same position of t.
Yeah, I just kind of.
Yeah, that would be an assumption that I would make. But if it came up in your mind, then it must be important. So keep on.
I mean, I just kind of 4 minus 4 equals 0, but that's so not true because.
What do you mean?
H of 2.
Yeah, h of 2. Okay, so you have 2 squared minus 4. So what's the value?
4 minus 4 equals 0.
Yeah.
So
if you were to write, h of 2 equals
0.
That's it.
Okay.
That's the y value. If you were to graph that as a point, what would that point be?
That makes more sense now. Okay.
Yeah, it would be 2, 0. You don't have to do all of them.
Oh, okay.
Why don't you do like number 2?
Mm-hmm.
I don't want you to do y plus 3. That's something a little more advanced. Let's just do like q of 3.
Okay. Q. Did you say B? Q?
Yeah.
Okay.
Yeah.
So we have Q of 3, 1 over 9 minus 9.
So what happened there? Yeah.
1 over 0.
What does that mean when you get that?
1 over, you can't have 1 out of 0.
Right. So it's a whole. It does not exist.
Yeah.
I usually write D and E next to it. Does not exist. But so that's actually a domain restriction right there. If you think about it, like there would be an asymptote right there. If we had if we had Desmos, we could graph it right now. But
I'm on iPad over there.
It's okay. Like we could even, I mean, if you want to.
Oh, it's in my room actually.
Okay, let me push. Okay. Anyway, let's graph that. 1 divided by x squared minus 9.
Is that just literally what you put in this?
You put y equals. But I have found that you don't always have to put y equals into Desmos. I was using somebody else's iPad.
1 divided by? It did it by itself. That's so cool.
Isn't it awesome when it does that?
That is so cool. Okay.
Squared minus 9.
Whoa.
Okay. No.
What is that? How?
Okay. This is a rational expression. Okay, so not only can x not equal 3, it can't equal negative 3. Because what happens? It blows up. It does not exist.
That's so weird.
Yeah. So when there are domain restrictions, do you remember what domain means again?
Yes, X.
X. So if there are restriction means you can't go there, right, if you're restricted. So domain restrictions are places where the x can't go. And the reason it can't go there is because the function won't exist. And so then we put an asymptote there.
Nice.
A vertical asymptote. We can have horizontal asymptotes too. Yeah.
Yes.
All right. Oh, this one's good too. It's going to have
graph this one.
Some more restrictions.
You want me to graph it or?
Yeah, go ahead and graph it first.
Okay.
Let's just talk about it.
So,
let's see.
I just put y equals again.
Okay, now, isn't that tricky?
Yeah.
So what is it saying y is right there? Is it the dependent or the independent variable?
Well, it'd be the dependent.
No, it's the independent. That's why I'm saying, like, why did they write it like that? That was just plain mean.
Yeah.
Because we all know, and the nomenclature says, that y is representative of the function, right? Okay, but anyway,
that's really weird.
In this case, you just put x, okay? Don't bother with using y's.
Okay.
And this is important for when you use calculators and stuff. Like, sometimes you have to interpret for your calculator. No, not x equals, y equals. And every place that you see y, you put an x. Okay. So the Desmos understands what you're really asking it.
So, okay. Every place you see y, you put an x. Okay.
Because a rose by any other name would smell as sweet. Yeah.
I like how it... No.
Yeah. So maybe you should use parentheses. Or you can use that thing where it puts it already in the form of a fraction. Don't you have that button, maybe? Yeah, just use parentheses.
X plus 2? Yes. Plus 2. Oh, I did it. Okay. Where's the... There it is. Y minus... Or X minus 10, rather.
Yeah. You have to be smarter than your calculator. Okay. Whoa.
What the heck? That's a little bit creepy.
Why are you doing that? It goes to infinity, right? Okay.
I was just curious.
Yeah.
It really stays in the same spot, though. I mean, if you count like proportionally.
Okay, so let's think about that. When the numerator is getting big, say it's like 100 plus 2. This is the square root of 100 minus 10, so it's 100 minus, that's 90. The square root of 90 is kind of like the square root of 10, so it's like about 10 in the denominator, a little bit less, and the numerator is like 100, so it looks like 10 altogether. Anyway, the numerator is getting bigger much faster than the denominator. That's the first thing.
Yes.
The second thing is, we can't have any negative. Do you see any negative values of y? No. You can't even have negative values of x. Why is that? Well, the square root, the radical, you can't have negative numbers in the radical, because once you do, they become this thing called complex numbers or imaginaries. And we can't graph those. Oh, yeah, I hope it's still going. Yeah, so you only get anything in the first quadrant. Those are the only types of answers. So there's like a lot of domain restrictions. Domain restrictions for where you can't have 0, right? Because you can't have an answer in the denominator that were 0. So this for 10, x can't equal 10 minus 10 because you can't divide by 0. Look over here. Look. See? Asymptote.
Right there.
No. Yeah. And also there can be no negatives because you couldn't blah, 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 so forth. The domain is really important.
Yeah. Is there any more?
Let's just keep rolling. Oh, look at that. Here's the equation. X squared plus y squared equals 4. Do you recognize that equation? What is it?
I don't know, but I recognize it. I've seen it before.
Okay, well, you can put it in there or I can tell you.
I'll put it in here.
Okay.
X squared plus y squared equals 4.
Yeah. In fact, you and I even talked about it because you wanted to know about parabolas. But it's not a parabola.
Oh! It's an oval.
It's an ellipse.
Ellipse, sorry.
Yeah. Well, actually, it's supposed to be a circle.
It's supposed to be a circle.
But the range was not set to the same proportion.
Okay.
Yeah. When the x and the y squared are not divided by any number at all, the coefficient is 1, it becomes a circle. An ellipse would have some fractional coefficient.
The difference between an ellipse and an oval? I completely forgot.
An ellipse and an oval?
Yeah.
That's a good question. I mean, an ellipse has 2 focal points. I don't know if an oval has a focal point. I just plain don't know. I'd have to look that up. That's very unmathematical of me.
That's okay. I always ask you questions.
No, that's okay.
Okay, so that I guess that was kind of the calculator's fault because I mean we opened as soon as that graph, but when you zoom in, it changed.
But when that happens to you, you can kind of notice that the x and the y's are not set to the same. Like, I don't know, the distance is not the same. And 4, it equals 8. Oh, yeah, that number right there, the square root of 8 is the radius.
Oh, nice. Okay.
Yeah, if you put 9 in there, you could count that the square root of 9, which is 3, would be the radius. Whoa. Maybe not that big. Yeah, okay. Okay.
100.
Let's see, how many minutes do we have? I wonder. I don't know. Do you want to look at polynomial functions just for a minute? Or no, let's just finish right here, I guess, with this lesson. They have just a couple more questions. Write the area A of a circle as a function of its circumference. Holy smokes. Let's decode that. Yeah, let's decode that for a second, because that had a couple of vocabulary words. Okay.
Circumference.
So, area, circle, circumference. You should write those 3 things down.
Area and circumference. And area is pi r squared, and circumference is 2 pi r.
Yeah, write those equations down. That was really good.
Pi r squared.
Yeah.
And the reason I remember that is because if it has the square root in it, it's the area.
Okay, so then it says, write the area as a function of circumference. So which is the independent, which is the dependent?
The area as a function of its circumference. The circumference. Ooh, that's not. I think the circumference, right? Because you.
Is the what? Circumference is the what? Dependent or independent?
I think it's
area. Yes.
And the area is the
area is a function of the circumference.
So A of C. Okay. Yeah.
Okay. So how can we do that?
Is it the same principle as f of x?
Absolutely.
Okay.
So
we did that a while back. Let me go look at what we did and see if I can. Where was this? It's back here. I know it is. I remember that vividly.
Gosh, we have talked about it. I don't feel like time has really passed that quickly, but you got a lot of stuff written down.
Yeah. It's somewhere. This is where we talk about set notation. Did we write it down on one of your papers, maybe?
Yeah, maybe. Here, let's just go back. And I think you're thinking of composition functions, but it doesn't have to be that hard. So what you need is this. Okay, you need something area you know is pi r squared.
And
so
is it just
wait. So we need to do something to this.
2 pi.
So what if I had circumference and I divide by 2? That would be the same as 2 pi r divided by 2, right? So then I would just have pi r. Is that closer to what we want?
Yes.
Now what are we going to do?
Yes. Is that?
Well, we got to make something with this. We got to make something with this to turn it into pi r squared.
To turn it into pi r squared?
Yeah.
Why do we want to turn it into pi r squared?
Because we need A as a function of C. Yeah. Oh.
It's, A as a function of C. Okay.
Yeah.
We divided by 2. We have pi r. Okay. So.
Yeah.
Yeah, that makes sense.
So if I say circumference divided by 2, I get pi r, but we're going to have to square that r.
So we have to square the r. I don't know what we can do to get that. Other than just like squaring all of it.
Well, let's see. Maybe what we need to do is also remove the pi. Let's just see. We're going to remove the pi. Okay.
Divide it by 2.
We're going to divide it by 2 pi. And now we just have r.
R. Square it.
And then we square the whole product, right? So what if we have c divided by 2 pi, and then we square the whole product?
Then we'd have r squared.
That gets r squared. Okay. And then what if then we put the pi on the outside?
Pi r squared. Oh, but
that's area, right?
Yeah.
And that's a function of c, right? I got rid of all the r's, didn't I? And now I only have c's. Oh, I'm so flippin' tricky, aren't I?
My mind was kind of blown up.
But, Okay, so unraveling this was like, what, this represents a lot of good concepts. Like, what do I really want? What is my end state? You know? A with only C's, not R's. Which I think that you were like, you understood from the beginning what that means, but then it's hard for you to conceptualize.
Yeah, you're much better at like you have creative ability. Like, oh, I can take this other thing and add it into this. That's almost completely unrelated. Like the quadratic equation and the polynomials the other day. Yeah, that unrelated, but you just
but I don't think that that's a big problem. It's just experience allows you to be more flexible.
Yeah, I feel the same. I feel like maybe all this like this EOI stuff has been drilled in my head. I can't.
What's EOI?
End of instruction. It's like the state testing at the end of the year, and we basically just learn to the state test. Like they only teach us stuff that they know is going to be on the test, and
so you kind of lose. Like nobody investigates much.
Yeah. It's just kind of like, okay, here's a quadratic equation. You have to know this. This is how you graph things. This is going to be on the test. We don't skip around. We don't have time for other things. We have a strict schedule.
Yeah. Kind of pacing of it. Okay. Okay, so what did we talk about today? We talked about domain, range. We talked about what a function is, how to identify with the vertical line test. We talked about a little bit with domain restrictions and what they do to the graph of the line, or whatever type of line it happens to be. And we talked about a little bit the square root, the radical, the rational expression when you have x in the denominator. So that was a lot, actually. Okay. All right. I feel pretty good.